Today we'll be working on the following problem. Let x and mu be a measure space with the measure of x is positive, and the g is a function from x to real numbers. G is a measurable function. Suppose that for any f integrable over x, we have f times g also integrable. Then we want to show that there must be some k such that a g is bounded by k almost everywhere. So pause the video if you want to work on this problem by yourself. Okay, let's prove this. So basically we want to prove this by a contradiction. So in order to do that, suppose not, right? So suppose not. So that is to say, like, so we can have, for any n, this set x in x for which g of x is greater than n has a positive measure, right? If it's not bounded almost everywhere, then we must have this en, the sequence of en, that has a positive measure for all n. Now we notice, like, we can write down like a en. Basically, it's the union of, let's see, m greater or equal than n, and x for which, like, g of x is bounded between m plus 1 greater or equal than n. We can write this, right? Okay, to make it exactly the same, we can put greater than or equal to n. So this en is the countable union of each of this set, right? So if we assume en has a positive measure, then one of the m, when m greater or equal to n, one of this must have a positive measure. So, and then we can increase this n. So, which means, okay, so we can have a sequence of, let's say, a sub n. And then it also will make a n increasing, right? Such that this set x for which a n less or equal than the absolute value of g of x less or equal than a n plus 1 has a positive measure for on, right? For any n. Okay, the reason we're doing this is like because we want to prove by contradiction. So now our task is trying to construct a integral function f such that f times g is not integrable. Then we reach a contradiction, right? So now so our task, we know this set. So now we know this set. Oh, we write this to be, let's see, f of n. So we know each f of n has a positive measure. So we define our f of x in the following way. So we define f of x equals to, because when x is in some fn for some n, right? So you can see like each the fi and fj, they are disjoint, right? They are disjoint, and the a sub n is a sequence of positive, we can say even positive integers, and then it's increasing, and then each so from the construction we can say a sub n is greater or equal than n for on, right? From the construction we can make this happen. So if we assume that we assume this, right? We assume this. So now, so x must be in one of the fn, or otherwise it's not in any of this fn. It must be like g of x is less than or equal to a1. Then we define this to be 0. And then if x is in some f of n, so here we want to define this. This is n to the 3 over 2 times the measure of f sub n. So because the measure of f sub n is positive, so this makes sense in the denominator. But now the in the denominator we just define to be g of x over g of x, the absolute value. So this is nothing but it's just a sign of g of x. When g of x greater than 0 is 1. When g of x is less than 0, it's minus 1, right? So because we know this by assumption, this makes sense. The g of x is greater than or equal to a sub n on f sub n. So it's a positive. So this makes sense. So now all we need to do is say if this is a counter example to our condition, meaning like we have to verify like whether, first of all, f, the integral of over x, this is because each f sub n is disjoint, right? So this we can integral of this f, the absolute value of f over each fn, and then we sum them up, and then because the other than this f sub n is always 0, so this actually n from 1 to infinity, and the absolute value of this guy over g of this and to the power of 3 over 2 times the measure of f sub n, and then take the absolute value, right? And now we know that the denominator becomes 1, and then these are all positive, all also times, I forgot this, over, because that's a constant, basically a constant on the set of f sub n. So when you integral them, you just use this constant times the measure of f sub n, right? And this is actually from n to infinity. This is 1, right? The absolute value 1, and then you cancel out this, so it's actually n to the 3 over 2, the reciprocal, and then you sum them up. We know this sum of the series is convergent, so this is convergent. So this means f is in L1, right? Because the absolute value of f, the integral over, is finite. However, but f times g, if we do this, And the same thing over here, right? From 1 to infinity. And now in here, f times g, f is this times g. So, and then take the absolute value. This becomes this g of x, absolute value divided by n to 3 over 2 times mu n times mu f of n. But here, this over, let me write this. Okay, so this, when you integral this, and then on each f of n, this becomes g of x. But g of x is on each f of n, we know on the f of n, g of x, the absolute value g of x is greater or equal than a sub n. So we can replace this with a sub n, and then this is greater than or equal to this, right? So which give us this cancel out a sub n over n to the power of 3 over 2, but this is greater than or equal to. But this is also greater than or equal to this, because we know this a sub n is greater than or equal to n for every n. So this n over n to the power of this, which is 1 over n to the power of 1/2. And this, we know this sequence diverges. So we found like this f is a contradiction, right? To the condition, because we found f, which is itself integrable, but f times g is not integrable over x. So our assumption is wrong. So which means like we find some k, right? We find some n or n, like this e sub n must have a zero measure. So we're done.